And so, okay, I have a bit the problem that I don't know you at all. Well, a bit from the presentation online, but not so. So I just try, and I hope I get some feedback so that I can a bit adjust of what I should tell and what I should not tell. And let me start with a definition. Yeah? Um, and then try to talk around it. So what is this category? Yeah. So we take a G, a semi-simple Lie algebra. Always complex, and then we take H, a Cartan subalgebra, and then we take R plus in the system of roots, system of positive roots, and then already one blackboard is full. Now let's see. I'll try to adapt. And then to this data, we associate a special category of representations. This is this category O, so it depends on the algebra and on H and the system of positive roots, and it's defined to be all representations of this Lie algebra G, complex, yes, and they should be finitely generated over B, and they should be locally finite for B, and let's say that for B is the Cartan and the sum of all the weight spaces where alpha is a positive root, we call this as well. That's why it's called B. And locally finite means every vector should be contained in a finite dimensional subspace stable under B. And the last is semi-simple over A, which should mean every semi-simple H, which should mean that every element of H acts as a diagonalizable endomorphism of A. And now this is sort of the first question, yeah. Well, I used sort of lots of things. I based myself essentially on Humphreys. Yeah, I mean, if you or say there are books on these matters. They basically say what is the semi-simple Lie algebra, what is the Lie algebra, what is the Cartan subalgebra, and now I cannot give a course on that. Say in 5 days it would be sort of ridiculous. So I have to essentially assume that you know all of it. But I mean, there is a way out. There is a way out. Namely, in fact, there is only one example, and this simplifies matters. I mean, essentially, the only example is you take S, L, and C. So matrices with zero trace, and then you take inside the diagonal matrices. SH, those with trace-free diagonal matrices. This will take G. And this B here, this B would be then the upper triangle dimension.
So in the definition of B, it should be alpha and R plus, right?
What?
In the definition of B, it should be the assumption over R plus. Thank you.
Perfectly. Yeah, absolutely. And in a way, the whole theory sort of only complicates matters to slightly more general situations. But it's sort of much work to do this. And still this guy is pretty much complicated. And then there is another way to chicken out. Namely, you could also pretend that there is only one example where you take SL2. I mean, this is already sort of sufficiently rich and complicated so that we can, and in fact, in a way, the essence of the whole theory I'm going to explain is that you have to study SL2 in detail, and then the whole rest is sort of like a undisturbed supercomposition of SL2 cases. And that is a bit a problem how to mix these SL2 cases, but in a way it's nothing else. So SL2 is really the guide to calculate it, understand? And this is what makes it so nice that you have an easy example. Yeah? And okay. And then the other thing is sort of to understand why the hell you should study this. Yeah, you could find lots of representations of Lie algebras. And why would this be such a sort of interesting one to do? And in fact, the letter is an O, and it was introduced by Gelfand and Bernstein. Two Gelfands, Gelfand, Faber and Son, and Bernstein. And O means something like basic. There's some Russian word which I cannot pronounce, Ofnovshochke or something like this, which means basic. And so this is a basic category. And so why is just this category so interesting? Well, it turns out that it's sort of a relatively easy modal case. I mean, it's almost, and we will see this, yeah. It's almost say representations of GLNC and the like. So here. So continuous representations of this group in Hilbert spaces or Banach spaces, they're extremely close to so you can, by understanding this category, understand these guys. And it's also, so this is the first reason. And the second reason might be, my second reason I want to put forward, that it's almost the geometric algebra. And I will try to explain this. And the last reason is that it's relatively simple. Okay, and today I will concentrate on sort of the representation theoretic side of the matter, and so suppose that you know all these kind of things, and try to explain a bit what this is, and maybe discuss examples. And maybe so the first thing, I mean, we need some object of O, yeah? So the first statement I want to prove is that all the so-called Werner modules are enough. And what are these Werner modules? Well, so if you take this Cartan and take a linear form on the Cartan, on these diagonal matrices, then you can also associate to it a one-dimensional representation. So this is a representation of the Lie algebra H. Just a one-dimensional representation, and every say a vector H acts on this standard vector here, call it 1 lambda, by multiplying it with lambda of H. So this is the one-dimensional representation of H. And now certainly there is a surjective homomorphism of Lie algebras killing all the root spaces. So this one-dimensional representation of H is in fact also a one-dimensional representation of the upper triangular matrices. Just the truly upper triangular matrices just act as zero. And then we can induce it up. Or I prefer to say produce it. So this representation of the Lie algebra is a module over the enveloping algebra. And we tender it up to make a representation of the whole Lie algebra. So I'd like to say that it's the produced representation, produced from B to G, lambda. And this is the so-called Werner module. And I mean, in Humphrey's book, they're called, I think, universally cyclic modules or something. I think. Universal cyclic modules, I think. And I think he calls them now, I'm not sure, maybe Ziegler. But a long time that I read Humphreys. I mean, there's a problem with this Werner modules. Katz would have liked to call them Katz modules, and it would also be appropriate. But I mean, Katz has lots of things, yeah. So whatever they call Werner modules, and maybe we should look at one of these Werner modules really in the eye, yeah. SL2 is always good. So let's try to have a look at so but these are all these guidelines. Yeah. And so let us look how it looks like. So well, we know that SL2 has a basis E H F, and this is this vectors, and this is this one, and this is this one. And they will appear quite possible. And then we calculate a line L, and we define with the commutator of H and E is 2E. The commutator of H and F is minus 2F. And the commutator of E and F is H. Find the calculator of this. And now we recall the Poincaré-Dolkoff-Witt theorem, which will tell us in this case that U of SL2 has a basis, enveloping basis, algebra, yeah, has a basis. F to the something, H to the something, E to the something. Yeah, all these expressions form a basis. Now, I didn't tell you what the envelopment algebra is, but I sort of declared that what is in Humphreys, we know it. Okay, so this and here all these natural numbers. And similar of B, or these two of B, has a basis just E to the H to the M, E to the L. Okay. And this means that the Fermat module with highest weight lambda has a basis f to the n times or tensor time, maybe times v lambda. And this v lambda, I mean here inside we have one tensor of 1, with an element of this kind of product. And this is an element of this kind here. And we call it v lambda, the highest distinguished sort of highest vector on this. So this Fermat module looks sort of pretty simple, right? This is the idea, yeah, pretty simple. This is why I started category O, because it's supposed to be simple. Okay, so for n equal to 0. So this is SL2 case. So let me I mean these blackboards are really sort of for smaller people. I don't know how Jakob does it. Find some water. It's good. I know that in Germany I would always write it with water, but here I see these electricities which are there, which makes me a bit skeptical. I don't know, but that's well, let's see. So okay, so here we have this Fermat module, yeah. So here the basis, yeah. I have v lambda, then I have Usually I would go downwards, but no. Let me. I will be a bit disturbed, but I go left. I have lambda, 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 and so on. Yeah. So this is the basis of my Fermat module. And okay, so Hx here, Hx is multiplication with lambda of H. Right? This is a number, and it acts by multiplication with this number, and then you calculate this, and you find that H here acts by multiplication with lambda of H minus 2. Let me just write lambda for lambda of H, yeah? So H acts by multiplication with lambda. So in this case, lambda is just a number, complex number, and this complex number is the value on this distinguished element here. Yeah, so let's think simpler. So here it acts by multiplication with lambda minus 2. This is because the commutator of lambda H and F is minus 2, and here by lambda minus 4, and so on. And now how the operator Fx is here anyhow. Here the operator F. And now the only problem a bit is the operator E. Now we know that E should kill the highest weight vector, right? Because the positive root vectors, we just declared them to kill this part here. Right? This was part of the definition. So the E would kill this, map it to 0, and then the next E here, what would this be? Well, I should say that all these guys are eigenvectors of H, and F has to put the eigenvalue 2 down, and E has to put the eigenvalue 2 up, because we have this this rule, which means in the enveloping algebra, the rule means that E H minus E H is 2E, which tells us that H E is E H plus 2. Right. So the E has to map this vector to a multiple of this vector. But the only problem is which multiple is it? And this now we have to calculate like hell. Yeah, this is sort of a nasty formula with some factorials and whatever. Yeah, so this is sort of so more complicated. And okay, I mean I don't know this formula, and here similar. Yeah. So the E goes here with some scalar, yeah. Okay, so this is the way this Verma module looks like. And now let's assume we have the for simplicity we have the highest weight be 0. Okay, just a simplest case. So lambda is 0. Okay, lambda 0. And in this case, what do we find? We find that E F V lambda. So on this we apply E. What should this give? This should give EF V lambda minus F F F E V lambda, right? But F E V lambda is 0. We know it. So it should be H V lambda. So it should be lambda times V lambda. Ah, wonderful. So we just calculated the general, yeah? This E here, will be the multiplication with lambda. So this vector will get off time lambda times this vector. This is what it will do. So we see that that there is one particular case when lambda is 0, then this vector goes to 0. Okay, very good. And so if lambda is 0, then so where's the kind of let's call this to get some place. So lambda is 0, then this gamma module goes on to the trivial one-dimensional representation of the whole unit graph. Right? On this now everybody acts as 0. And then here is a kernel. Here is a kernel. And when we calculate like hell, we see that, well, the kernel has to, well, here's a kernel. And the kernel has to be a quotient of the Balmer module with highest weight. I identified the weights with their value on H, yeah. So it's just -2. Yeah. But now it turns out that this module is simple already, and we didn't check it. So then this is even an isomorphism. So we have a short effect sequence. The Velma module starting here goes to the Velma module starting here, and the quotient is a trivial thing. Okay. So let me yeah. And I mean, in fact, this guy is the trivial, is the simple representation with highest weight 0. So we might write it like this as well. And maybe it's better. Maybe it's better for me to fix to just for notation to say rho in H dual is defined by rho on H is 1. Now, this is in the case SF2. In other cases, it's a little bit more complicated. So we have here minus rho, then I have here the top. Nice, like this. Looks more natural. And okay. And now sort of in the same vein, yeah. In the same vein, when we move lambda, sort of for most lambda, this is just an irreducible module, because none of these maps will ever be zero. But there are sort of very special lambdas where it's not. And this is when we have an integer. So we have, say, lambda n rho will be a quotient. So this is a representation of dimension n plus 1. Yeah. So this is an irreducible representation of dimension n plus 1. I mean, we should know that the irreducible representations of SL2 are classified by their dimension. And also this here, so we have the irreducible representation of dimension n plus 2, which is a quotient of this Verma module with highest weight n rho. And the kernel will have highest weight minus n minus 2 times rho. And this is, in fact, the only case where a Verma module is irreducible, is not irreducible. So all other Verma modules in this case are just irreducible. There's a lambda irreducible for a loop. Okay, so we saw already a hope that for SL2 it's not so bad. Yeah, we can draw this kind of picture and then analyze where this chain breaks moving up, and then we get as a quotient the finite dimensional representation, and there's a submodule, another Verma module. And this is okay. So yeah, and the problem is a bit that in general it's sort of similar but much more complicated. So here we have the Verma modules. I have to kill them. Okay. Okay. And the next thing I want perhaps to explain all Verma modules have lambda have a unique simple code. Well, this is sort of doubt because by definition the Verma module is cyclic. Nah, well, maybe it's not so dull after all. I just wonder about a cyclic module. Need not have a unique simple quotient, right? Okay. I mean, a ring has not necessarily unique simple quotients. But a Verma module does, and And the reason is the following, that like here, yeah, we have this unique sample approach. And the reason is that this gamma module, I should maybe say what the weight space is at the end, yeah. So if we have an object or representation anyhow, yeah, V, why not of H? And we have lambda linear form on H, then we say lambda, it's called weight space, yeah. This is the set of all vectors such that H times V is lambda of H multiplied V for all H. So it's the intersection of all the eigenspaces of H on M with eigenvalue lambda of H and H runs through H, simultaneous eigenspace. This is called the lambda weight space. Wait. So here we have a one-dimensional lambda weight space and a one-dimensional lambda minus 2 weight space and so on. And if this thing is an object of the category O, this N, N is O, then by definition, M is the direct sum of the weight spaces. But this is just what this condition H semisimple means when I write it out. And now this state, I leave it a bit up, namely delta lambda as a maximal submodule. Say I should say cos no proper submodule me every proper submodule and inside as N was contained the direct sum of weight spaces which are not lambda. Yeah, each submodule, if the whole thing decomposes into weight spaces, then the submodule also has to decompose into weight spaces. It's clear from linear algebra. And if it meets the highest weight space, then it contains generator, so it will not be a proper submodule. So every proper submodule is contained in the sum of the other weight space, which is not the highest weight space. And And then this is clear that there's a maximal proper submodule. Just the sum of all proper submodules. Still a proper submodule. This be the maximal proper submodule. And so it has a maximal proper submodule, a unique one, then also a unique simple quotient. Okay. We have seen it a bit as a two case, and every submodule, every proper submodule are not equal. Okay? So I know that. It's a unique simple quotient, and this is called like L. And you might be used to this because this is the standard construction, algebraic construction of the simple irreducible representation of these finite dimensional semi-simple D algebras. So what should be written in Humphrey somewhere? Would be that dominant integral weights, whatever it is, x plus, this is subset H dual. They go bijectively to finite dimensional irreds of this E up to isomorphism, and for every lambda we take this unique simple quotient. This is the classification of the finite dimensional irreducible representation of the diagram, which is a part of category O, and these are so they constructed as the simple quotients of the Werner module, just in the same way as we did it for SL2, right? So in case SL2, if G is SL2, then this X plus is the multiples of rho. Yeah, and we have seen how for multiple of rho, the Werner module with this highest weight has a finite dimensional quotient, which has first dimension n plus 1 or something. This is the way to construct all the irreducible representations of SL2. Okay. But now this is maybe the third statement. That the irreducible object of O, so say H dual, is in bijection to the irreducible object of O. So this would mean irreducible objects up to isomorphism by mapping lambda to L of lambda. This unique simple quotient. And we have seen for SL2 the situation is very easy. Right? In this case, the weight is a multiple of rho. Then this unique simple quotient is finite dimensional. And in the other cases, it's just a Werner module itself. So it's kind of cheap. But in general, it's much less cheap. And yes. And why is this? So let's maybe prove it. and check the time. I talk 3/4 of an hour. Okay, I will still check it and then we make a definition. Well, if you can prove it from what I know, then I make the intervention right now. So let's start again in 10 minutes, okay? 28.
Maybe not for maybe not for maybe not for other people. For tiny different mistake, I mean, some of
Okay.
Wait, that's the question.
Yeah.
Are you writing F or H for the calculus? Yes. Algebra.
Ah. Yeah. This is a good question. This is a good question. This symbol is supposed to be a script Zitterlin H.
Okay.
Which is sort of, I don't know. I mean, there was a period when Germans thought that to write Latin was sort of not national enough. So they invented new letters, which sort of more like rune kind of thing. So there is an A, B, G,
Yes.
and an H, and this is those which are used for the diagraph. And the F, I would write it like this, but this is not Zitterlin. And I don't know Zitterlin so well. I mean, an E would be like this, but I don't use it. I write an N like this. Well,
I just asked because it's how I write F.
If you write it like this.
Yes.
Yeah. Yes, I understand. I mean, anyhow, the alphabet is not big enough for mathematics.
Sorry, is there an analog for Greek letters as well?
No. Okay. No, but they invented these Zitterlin things and well, for mathematics, it's great that they did it, and then they switched back or whatever. So I cannot read the letter from my grandmother because. Okay. Yeah. Okay. Other question. Not for the moment. So. Yes. So I tried to explain why every simple object is a quotient of the Wehrmann module, and what I should maybe discuss a bit before. So this is maybe 0.4. I was too early, yeah? So this is 4 maybe. So then 3 might be that the dimension of yes. If V is a representation of P, and the dimension is finite, and it's H simple, linearly simple, then if I take this representation U of G tangent U of B, this is also a no. This induced representation. Yeah, in fact, I didn't prove that the Werner module is in O. I just realized that I didn't prove it at all. So why is this in O? I mean the point is, I mean that it's finitely generated over G via that is locally finite over B is clear as well, right? This is a union of finite dimensional subspaces, and then these tensors are sort of stable under B. It's also clear, and then it's a semi-simple over H. It's also clear because I asked it semi-simple V to be semi-simple over H, and then I multiply root vectors, and I just change the weight, but it stays semi-simple. So all this is clear. So this thing is in O. Okay, very good. And I mean, let me tell you, it even has a delta flag. I mean, a filtration where the subquotients are all Werner modules. And why is this? This is because this Lie algebra B is solvable. Right? It's a solvable algebra. And so V has a filtration with one-dimensional subquotient. So it's 0, it's B0, it's B1, Bn, B, and all the subquotients are one-dimensional. So out of this form, yeah. This is whenever you have. I mean, if you have a solvable Lie algebra, yeah, a finite dimensional solvable Lie algebra, an arbitrary solvable Lie algebra, but a finite dimensional irreducible representation, then it's of dimension 1. So the finite dimensional representation of B are all of dimension 1. So this finite dimensional representation of B here has a change where all the subquotients of dimension 1. And now what could be, now you have to check that B, the derived Lie algebra from Euclides, is the strictly upper triangular matrices, the alpha nu r plus, which is sometimes called N. So these guys on all these one-dimensional representations have to act trivially. So they are just these C lambdas I had before, yeah, with some weight. So that's C lambda 1. So there's such a filtration, and then I use it up, and then I get a filtration on this guy where the subquotients are Werner modules. Okay. And now even better, this is now 4, or I get far away. 4, every M and O is a quotient of such a guy. Why is this? Well, you see, we know every M in O is finitely generated. And we know B acts locally finitely. So it's finitely generated by a finite dimensional B stable subspace. Yeah, so U3 times V, and this is a finite dimensional B stable subspace. And there it is. You just take the multiplication, and this is then a surjective homomorphism. Okay. Okay, very good. But now things are getting easy. So every simple object has to be a quotient of such a guy. I don't know. I mean, a simple object is just generated by a one-dimensional plurality or something, and this doesn't trust. Okay, so this is also check. I still didn't check that. Did I check that this is actually so? Yeah, check. Okay. So I'm pretty well. So the next thing I want to show is that I'm nearing the end of this sort of I want to show now this is maybe 6. Every M and O has finite length. Well, this is slightly more tricky. I mean, it would follow at once if we know that Werner modules have finite length. Yeah. But why do Werner modules have finite length? Well, there's an easy way to chicken out Humphreys. But since we will need the center of the enveloping algebra anyhow, let me give a proof. So I think maybe I can now.
Before you read, so earlier you said this delta of lambda is mostly irreducible by the sum, right?
Yes.
Can you say again how this relates to this 0.5? Is L of lambda then?
Then L of lambda is equal to delta. Yeah. So most of these guys are actually irreducible.
What does most?
Yeah, what does mostly mean? So for SL2, it means the quotient is finite dimensional. So if lambda, so for SL2 mostly means so if G is SL2, then delta lambda is simple. If and only if lambda is not a dominant value, so not a positive multiple of rho. So either it has a finite dimensional quotient, which we know, and the highest weight is the same as the highest weight of a finite dimensional, which is or it's irreducible. And so mostly some, but in general, the mostly is a bit more tricky. Okay, so let me find this out and explain about finite length. Well, I mean, we will need the center of the enveloping algebra anyhow, so I will not be cheap here. Now this is sort of a tricky business with algebraic geometry and so on. Let me just try to put down a correct statement. Mm, mm. So, mm. So a big player in this theory is the center of the envelopment. So this is the center of the enveloping algebra of G. This is a big player in this whole theory, and there is something called the Harishchandra isomorphism, which gives an isomorphism from the center. I like it the other way around, I guess. So we take the regular functions on H dual and take the invariance for the dot action of the y. I have to explain how this. This goes isomorphically to the center. And I prefer the other way around. Right. And so and it is characterized by the following property. First of all, I should tell you what this is. Yeah. So H dual is the dual of the kata, the space of weights. This O means regular functions. Yeah. So polynomial functions on this finite dimensional vector space. Now W means the value. Now, this again is a thing which is in general a bit complicated to explain, but in case if you don't know it, I will not explain it. But in case when G is at Ln and H is trace-free matrices, then this is just the symmetric group switching the entries of the diagonal matrix. Yeah, so this is the Weil group in this special case here, symmetric group switching the entries. It's always a reflection group. There's a whole theory behind, but what can I do? And now I prefer to I mean, there's some questions about whether one should use a dot here or not. But I like to do it. I mean, this is also isomorphic, certainly to the just invariant functions, yeah, invariant. So it would be symmetric polynomial in this case. Yeah, and the invariance is by translation, and this dot action is given by x dot lambda is lambda plus rho, and then apply x, and then subtract rho again. So you have sort of the same action, but the fixed point is rho minus and rho is a half sum of positive roots. So there's a shift, so rho shift, yeah. And here this is just translation by rho, yeah. Let's call it plus rho, and this one that. Or minus rho, depending on the direction. Maybe I'm wrong in the direction. I'm always getting confused. And so in this case, as I say, it's symmetric polynomial. And why it's an advantage to have the morphism to this sort of dotted action? Well, it's because then it's given as follows that C of a central element applied to lambda times V lambda is Z times V lambda. And this is here, V lambda is the generator of the Gamma module. So in this case, you see, so to characterize this homomorphism, yeah, what do I have to do? I have to take this image of Z and evaluate it at a point lambda and know which color I get. And I want to say this is just the scalar by which this element Z acts on the highest weight vector on the Werner module. It has to act as a scalar because the highest weight space is one-dimensional. So it has to act by a scalar. But which scalar is it? Well, this color. And you see, this row shift is a nuisance, yeah? And there are several ways sort of to get around with it. Yeah. For example, you could make this formula ugly, yeah? That you put a plus row in here and omit the data here. Yeah. Or you could make the definition of the Werner module ugly by saying the Werner module delta lambda has highest weight lambda plus row or something, yeah? And all these different ways to get around this problem are sort of available in the literature to better confuse us. But the row shift is sort of a fact of nature, and which fact of nature actually is it? I mean, where does it? Well, now this is a philosophical question. Yeah? Certainly, one had to prove these kind of things. This is called the Harishchandra argument. Andra isomorphism. And where does this fact of nature come from? Well, not now. That's a philosophical question. It's not a good moment to ask it. And it comes from something. There is some of you might have seen something called the Chevalier isomorphism. Which could be written like, if I take a semi-simple Lie algebra and I divide it out by the action of its group, it's like having the Cartan and divided by the Weisel. This is sort of the quotient in the sense of invariant theory. And it could be written like, take the regular functions on G and take the invariants and restrict. You get regular functions in H and the Weisel invariant. And this thing is called Chevalier isomorphism. And is a fact of nature. In fact, in the case of GLN, it sort of specializes to the fact that if you have square matrices, you have functions on square matrices, and you want functions which are invariant under conjugation. Yeah, what is it? Well, the characteristic polynomial. You take the coefficients of the characteristic polynomial. This is all, and this generates all these functions. And this is just sort of the symmetric functions at the eigenvalues. Yeah, so this is what this burns down to in GLL, but sort of easy, and more general, right? It's getting more complex. And then this can be massaged a bit to go to dual spaces. This is sort of not such a big deal. But it's a bit less natural, right? Because the cartan is sitting inside here, clearly, and then you can restrict functions. And here you have to say how to embed it in here. Well, not touchable here. And now this damn thing has to be sort of, this is finally the symmetric algebra of G. And this is the symmetric algebra of H, at least in characteristic 0, I think generally. Okay. And now sort of this gets transformed into the development algebra of G and the invariants. This is a non-commutative variant of this. And then you have to check that this is in fact the same. And this is sort of how I don't know. Then this homomorphism, you have to check that this is a homomorphism. This is not so difficult. And then to check it's an isomorphism, you have to filter the thing and take the associated gradient and say, oh, we end up with this. And if the associated gradient is an isomorphism, it was an isomorphism in the first place. So, okay, it's business, yeah? It's sort of non-trivial business. But now let's assume we know this business. And so we have in the other way, you can say we have a map from H dual modulo the dot action of the Y group gets isomorphically to the maximal ideals of these. Yeah, this is just, see here we have a homomorphism of commutative rings. This corresponds to a homomorphism of algebraic varieties. Yeah, this here is a quotient variety, more or less by definition. And this, and I don't need to make a double bar because this group is finite anyhow. So this is a variety of parameterizing orbits of W, B, and here. And this is the variety corresponding to this affine complex algebra. And the map is now if we sort of translate everything I said, yeah, then here I have H dual, and then a lambda in here gets mapped to the annihilator. No. Now this is a other rule of mathematics, teaching in particular, that the important things always want to get small. Let me try to find it, yeah. So this gets mapped to the annihilator of the Verma module with respect to the center. And this is sort of saying the same thing which I used at the definition of the Alexander homomorphism, but sort of reformulated, yeah? Tautologically reformulated, but I admit this might be complicated for sort of on the spot. Okay. So what do we see? Let me get back to SL2 maybe. let me get back to SL2. V SL2. In this case, the center, well, it's well, what is the center? I mean, it's regular functions on a line, symmetric around, which are symmetric around minus rho. Okay. So it's squares of, it's a polynomial ring, but in a variable square. Yeah. The variable should be the function which has its zero here. This is how it looks like. And this variable turns out now, damn hell, I don't even know. What I know for sure is that this is a polynomial ring generated by one element C, and this C is a Casimir. And if I recall correctly, but I'm pretty sure because I just checked it this morning. Here Fe plus H times H plus 2. And now I'm already not sure. H plus 2 or H minus 2. This is, about this I can check. It's good to have notes. Sometimes. Plus 2 for Fe. Yes. So this is an element, right, of the development algebra. And I claim that, but now this element kills the trivial representation, right? So the idea generated by it is the annihilator of the Werner module with highest weight 0. Okay, because this Werner module is killed by E, the highest weight. We have just only to look at the highest weight space. So it's killed by E and it's killed by H. And here's another Werner module which is killed by this. The Werner module with highest weight minus 2 rho. Because the highest weight vector, we have just to check on the highest weight vector. It's killed by E, it's killed by H plus 2. Okay, it's also killed by this thing. So we see that this highest weight 0 and this highest weight minus 0, these two Werner modules are killed by this maximal idea of the center. Yeah, and this is the only two. So it's already pretty clear. Now I'm in bad shape because I draw the Werner module starting from here to this side. So it's much better. I should write the 0 here and the minus 2 rho here. Yeah. So then I can tell you again that this Werner module has weights here. Here the F was going down, the E was going up, and so on. This was the Werner module delta 0. This has this central character here. Is killed by C. And if there's any other vector which gets killed by E, yeah, then this should be also killed by C. So the only possibility is here, minus 2 rho. Wrong picture. I go from 0 to minus 2 rho. Now the weights go down by 2 rho at every spot. So here we have delta minus 2 rho, which was the submodule of this thing. Yeah, which was because this was the highest weight vector. But this can have no, this has to be a simple module. Now we can see it. Because if it was not simple, it would have another vector killed, and this would have a wrong central annihilator. So no way. And in general, things are similar. Yeah, so if I have a, if I draw for you now a picture in the case of SL2, let me now draw a careful picture in the case of SL3. So SL3. So the first thing I have to draw for you is the root system. I mean, H is dimension 2. And in fact, it's the trace-free matrices. And we have 3 maps, epsilon1, epsilon2, epsilon3 from H to C. Yeah, the first, second, and third diagonal entry. All right, this is a linear bond. And the root system is all epsilon I minus epsilon j, where I plus j, I is not j. There's some checking to do, that this is the weights. And then if I in some metric, I draw this for you in the plate. This looks as follows. There, sort of complicated.
What do you mean I different from J?
Oh, I meant I different from J. Yes, absolutely. Yeah. And so I have, and they have the negative roots. Now it's not beautiful. So this is the way these looks can be drawn. Yeah. So here I have alpha, beta, alpha plus beta, the simple roots. Here's the positive roots. Okay. And I mean, alpha should be epsilon 1 minus epsilon 2, and beta should be epsilon 2 minus epsilon 3. And then I have here, the root system. And then I have this while group. And now I have to check what is minus rho. So I have to take the sum of these 3 roots and take half of it. So rho is alpha plus beta, right? Right. 1/2 of the sum of positive roots. Now I cannot choose alpha. This is dead. X by the delta is a positive root. So here will be minus rho. And now what will the while group do? Well, I draw for you the reflecting. This is a reflection group always. And the reflecting planes are orthogonal to the roots. So here, but now I draw them centered in minus rho, right? So I draw one of the things should be here. So this will be one reflecting hyperplane, and another will be orthogonal to this root. So it's here. And the third will be, so here I have the group generated by the reflections on these hyperplanes, and I just saw there is a course on reflection groups right an hour before my lecture, and I will use everything that they tell. And you can check that the group generated by these three reflections is a symmetric group, S3. So five will be symmetric with S3. And now I've drawn already too much. Yeah. So let me try to simplify things. So I leave out the roots. Yeah. So here I just have the dot action of the Y group. So here are the reflecting hyperplanes, and here is minus rho. And now, if I have a Wörmer with highest weight, say lambda, then the orbit of this lambda will have here these 6 points. Here, 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 and here. So this is W dot lambda. Yeah, the orbit of lambda under the Y group is these 6 points. And now the point is a simple module can only be a subquotient. So the thing is that in a Wörmer module with highest weight lambda, there can be a simple module as a subquotient only if the annihilator in the center of this simple module is the same as the annihilator of the Wörmer module, which is the maximal ideal endpoint. So this is the case if and only if mu is in the orbit of lambda under the reflection, right? So the only highest weights of simple subquotients of this Wörmer module lie at these 6 places. But now, why has the Wörmer module finite length? Well, because whenever I have a simple subquotient, I will make the weight space here dimension 1 smaller if I divide it out. Yeah, and so it has to have finite length. That's it. Well, so what did I want to say? So I could say the length of delta lambda is bounded by the sum of the dimension of the weight spaces mu, where mu is in the dot orbit of lambda. And so it's fine. Yeah. Okay. And so we know that every Wörmer module has finite length, and every object of category O has finite length. So in a way, it's a very small hyperproof. Yeah. Now what's the time?
The time for a break.
What?
Time's up now.
It looks like the time is up. No, not quite. 28. No.
Yeah, that's.
Yeah. The time is more or less up. The time is more or less up. Yeah. So maybe just have questions. And let me explain what I want to discuss more. Yeah, so what I want to do tomorrow is have a look at category O from the point of view of knowing that it's a finite dimensional, it's a category of finite length. Every object has finite length. And if we fix the central character, there are only finite dimensional simple objects. So, and in fact, there are even enough projective objects. So it's modules over finite dimensional complex algebra. Or it's representations of a quiver, a finite dimensional representation of a quiver with relations. Sort of automatically, yeah, this is generally known. So what are these quivers? What are these algebras in this special case? And I want to show that you can. They're just sort of nice, you know. They are. You know, I always have the impression sort of that mathematics sort of navigates the close line between the trivial and the impossible, yeah. And here it's just the falling case, yeah. So one can really say so. Okay, thanks for your attention. Very good question.
Very much. Questions?
Could also be asked after,
Yeah, whatever. Maybe during coffee or whatever.
Yeah.
Okay.